Technical indicators are not just useful for traditional technical analysis, but they're also relevant for machine learning prediction models. They condense essential information on price trends and momentum, which can enhance future stock price forecasts. They can also reduce data dimensionality, which can minimize the risk of overfitting, which is a significant challenge in high-dimensional financial data sets. This tutorial will show you how to get started with using technical indicators as features in machine learning models. We will use the Pandas technical analysis package to calculate 7 types of technical indicators on real-world stock market data. We will then create a set of models that backtest actual performance of technical indicators on future stock prices. This involves iteratively training the model on 4 weeks of closing price data, then generating predictions for the following trading day's closing value. This analysis will first model each technical indicator separately and then combine them all together. And we will use evaluation metrics such as the mean absolute error and mean square error to determine model performance. This analysis should be an entry point for you to do your own empirical testing of technical indicators on future stock performance. You can test different technical indicators with different parameter options, as well as different machine learning models and model training and test validation splits. And you can ultimately create more complex models that track stock price dynamics. Before we begin, make sure to like and subscribe to the Deep Charts channel for more machine learning and quant finance videos like this one. Start by opening up a Jupyter notebook in your code editor, and then import the following packages. We'll be using yfinance to pull historical stock prices, and Pandas-TA for calculating technical indicators, and a few other libraries for model creation, evaluation, and plotting. Next, we'll use the download function from yfinance to download historical NVIDIA stock data from the last 2 years. This data includes open, high, low, close, and volume prices. Next, we're going to lag each of these columns by 1 trading day with the shift function. This is a crucial step because we need to ensure that none of our created technical indicators include information from the same day or any future dates. For example, by shifting the close column, each row will now show the previous day's closing price. This way, when we calculate indicators like moving averages or relative strength index, they'll be based purely on data that would have been available at the time. This approach prevents future data from unintentionally influencing our calculations, which would make the model overly optimistic and unrealistic. With our lag structure settled, we can now calculate several key technical indicators that might feasibly be strong predictors of future price changes. This includes measures such as simple and exponential moving averages, Bollinger Bands, and the average true range. Note that we use the previously shifted stock price data for the creation of all of these technical indicators. You can learn more about these technical indicators in the video description below, but I also encourage you to seek out additional ones and test different parameters. Okay, so we've calculated our technical indicators and can see that they have been added to our data frame. We next drop rows from the beginning of the time series that have missing values, which resulted from our calculations. And now we can begin the modeling process by defining some core parameters. The window size variable is set to 20, meaning we'll be training the model on the last 20 trading days of data, or roughly 4 weeks. You can alternatively test different windows, but I chose this 4-week rolling window to help capture only recent trends in stock prices. So the model will sequentially move through the entire time series using the past 4 weeks of technical indicator data at each step to make predictions for the next trading day. Model performance will then be evaluated by comparing each predicted price with the actual price over the entire dataset. The average performance over time can tell us the extent to which each technical indicator is actually predictive of stock price performance. And that might inform us about whether we should actually trust technical indicator analysis. We will now create a list of indicators that will be fed into our analysis. This includes the previously created indicators as well as the previous day's closing price, and it will tell us whether the technical indicators outperform the previous day's price. We can now initialize a dictionary that will store our model results before starting the modeling phase. I promise that this next code chunk is much simpler than it looks. From a high level, we have 2 main loops. The outer loop iterates through each 20-day window training set and its corresponding 1-day test set, allowing us to move sequentially through the entire dataset. The inner loop then iterates over each technical indicator in our indicators list, training and evaluating a model for each indicator individually. We fit a model using ordinary least squares from the stats models library with the close price as the target variable. You could alternatively use other machine learning algorithms here. We then predict the next day's close price based on these indicators in the previous close. This inner loop essentially evaluates how each individual indicator performs as a predictor. Once we have predictions for each model, we calculate the daily mean absolute error and mean square error by comparing the prediction with the actual close price. Mean absolute error, or MAE, tells us on average how far off our predictions are from the actual values. The mean squared error, or MSE, places a larger penalty on larger errors, making it particularly sensitive to large prediction misses. I'm going to go ahead and run this chunk of code as well as the next one, which just calculates performance metrics. And we can then output the average results for all time windows, ranking each indicator by the lowest mean absolute error. We can see that the close shifted variable, which is just our previous day's closing price, had the lowest average error. This was followed by technical indicators such as the moving average convergence divergence and the exponential moving average. It might be surprising that the previous day's closing stock price was the strongest predictor. But it makes sense when we consider that recent stock prices are often highly correlated from one day to the next. The previous day's closing price provides a strong baseline, capturing short-term trends that many technical indicators take longer to recognize. However, the results will vary depending on factors like the stock chosen, the machine learning model used, the assumptions and parameters of the technical indicators, and the addition of other variables into the model, such as time trends, interaction terms between different indicators, and other theoretically relevant macroeconomic indicators. We can visualize each of our backtests using a data visualization package such as Plotly. I won't go directly into how this code works, but the output provides additional insight into the average error from each of our time sequential models. For instance, we can see that the mean average error for most indicators increases over time. This suggests that more recent days in this time series had more volatile market swings. Overall, this analysis is an entry point to get you thinking about how to incorporate technical indicators into stock price machine learning models. You can find the code in the video description below. And make sure to like, comment, and subscribe to the Deep Charts channel for more videos on how to gain insight into financial markets through machine learning.